So we're in Unit 7 talking about the mole, and now we're going to talk about another situation that would affect molar mass, which affects, in turn, our calculations. And this is a hydrate. A hydrate is a combination of an ionic compound and water molecules. So what happens is ionic compounds generally exist as a solid, but when they form, a lot of times what happens is water molecules get trapped inside of the crystal. So let's say we have a reaction and our cations and anions are coming together and making a compound, and they're doing it in a solution. So there's water everywhere. And so you might have this situation, and don't draw this. You might have this situation where it's forming crystal in 3 dimensions, but you end up with these open spaces because due to the positive and negative charges, you just can't fit anything in there. But what happens a lot of times is that you get a water stuck in here. And so here it is, and there's my water. Or you might have a situation where there's more than one. So let's say that this one's got 4 waters stuck in here. It's a possibility. And so this is the kind of thing that's happening. The solid is forming, and in the process, water is becoming trapped. So when the ionic compound forms a solid crystal, we have these water molecules that are being trapped, and the hydrate is the compound that results. A hydrate is a compound that has a specific number of water molecules, and they're all bound inside of it. When you calculate the molar mass of a hydrate, it's important to include the number of water molecules that are present in the crystal. If we forget about the water molecules that are trapped, we may end up with calculations that are off. We may end up adding too much of a chemical or too little of a chemical. So we just have to be careful and be aware that this is a possibility. So this is the type of thing that you might see. And we do this in the lab, and we'll see how it works out. But here's how it would typically work in the lab. We have a sample of calcium chloride. But calcium chloride is one of these compounds that tends to make a hydrate. And so I'm going to put a ... And I know it's a hydrate, but I'm not really sure right now how much water gets trapped in there. But there's a way I can figure it out in the lab. So let's write down the formula that we're really looking at here. So calcium chloride is an ionic compound, looking at its charges, and the ratio gives us this. Then, since it's a hydrate, we put this really heavy dot here, and then we would put in a number. If we knew how many waters were there, it would be the number. But for now, I'm going to make it just an X, because I don't know what that number is right now, followed by H2O. So this dot tells me that the waters are part of this overall hydrate, and this X is the coefficient for the H2Os. It tells me how many waters are stuck there for every CaCl2 formula unit. So here's the way it'll work. Let's flip to the next page. You don't have to draw this. I'm just going to give you an overview of what this lab would look like when the time comes for us to do it. So we've got a couple of different pieces. We've got a Bunsen burner, and for the sake of the picture, this one's already lit. We won't light it until we're absolutely ready to start the heat. But there's our Bunsen burner. Then we have this big piece called a ring stand, and its whole job is to support the ring. And the ring comes out here. It's got the circle. And on top of this is a clay triangle. And the clay triangle is just this support piece for the container we're going to put in. And the container we would use is called a crucible. And it's got somewhat rounded sides with a small flat bottom. And they're usually made out of porcelain. They pretty much the same thing as a coffee mug. You've got to be careful though, because they're extremely thin, and if you set them down on the counter too hard, they're liable to just shatter. And it happens every year. At least 2 or 3 of them go down. We're in the process of getting stainless steel ones as a replacement for all of our old porcelain ones. But so what we do is we put some of our hydrate inside the crucible. And we need to know a few things. We need to know what's the mass of this crucible when it's empty. What's the mass of the crucible once I put in this hydrate? Then I come up here and I put my crucible, and let's make it red so we can see it better. And I put my crucible in here. Here it is. And we're going to heat this up. And we're going to line it up so that the bottom of it is pretty well in the hottest part of the flame. And we're just going to heat it up really hard for about 10 minutes. Gentle at first so the temperature change doesn't crack the crucible, but it needs to be hot enough that we're that we're vaporizing all the water and allowing it to escape. Then once you're done with heating it up, you take it off using some special crucible tongs so you don't burn your hands. And then we find the mass of the crucible and the compound afterwards. So we end up with a few numbers. So we always subtract out the weight of the container. So we'll have a number that we call the mass of the hydrate, which was the original compound before we heated it. And let's say for this example that it was 5 grams of this calcium chloride something hydrate. After we heated it up, we'll find its mass and subtract out the crucible. And this is the mass of the anhydrate. And anhydrate means without water. And so you should have a number that is lower because we boiled off all of these water molecules. And so the anhydrate should just be CaCl2. There shouldn't be any water here. And then the mass of the water is whatever is left over. So 5 grams minus 3.76. And so you find that this is the mass of the water that boiled off from this compound. And so in order to figure out what this X is, that's the whole point. We want to figure out what is this X based on this experiment. So X equals, let's give a little more room. X equals moles of the H2O divided by the moles of the anhydrate. So that means we're going to have to change grams of anhydrate to moles and grams of water to moles. So if we calculate the molar mass of CaCl2, we will find 111 grams for every 1 mole. and that ends up being 0.0339 moles. And then the mass of the water becomes moles of water. So we're dividing by 18.0 grams, 1 mole. We have 0.0689 moles of water. These are the numbers that we're going to plug in up here. So moles of water, moles of the anhydrate, and putting this in your calculator, it's 2.03, which is very approximately 2. And I don't have a problem with rounding something like 2.03 to 2. It's very close. And also keep in mind that we are measuring these things ourselves. And so there's going to be a little bit of error. And so within a certain amount, this error is fine. And so we find that the actual formula of the hydrate, so we put X back in here, CaCl2, there's the big dot that tells me it's a hydrate. Here's the coefficient of the water, and here's the H2O. And so this tells me that for every 1 formula unit of CaCl2, I have 2 waters that were stuck in that compound. So here's how we can use this. If we are in the lab and we're working, and what I tell you is that we need 30.0 grams of calcium chloride for an experiment. So if we're basing it just on CaCl2, we found the molar mass, 111 grams per mole. But if this is actually a hydrate, you have to factor in these extra 2 waters. And so the molar mass would be 111 plus 18 plus 18. So that's the 2 waters. So the molar mass of this hydrate, which includes 2 waters, is 147 grams per mole. And here's how it affects us. If I think that I'm adding 30 grams of calcium chloride, here's how many moles it is using the anhydrate formula, and it's 0.270 moles. This is the amount that I think I've added. But look at the hydrate. If we convert this mass that we measured to moles based on the molar mass of the hydrate, 0.204. These are different numbers. And so one of these numbers represents the amount that I thought I was adding, and the other number represents the amount that I actually added. So I'm going to change colors here. So this one, this top number, we used the wrong molar mass. This is the amount we thought we added. And then you look at the hydrate. So this is what we thought we added, but this is how much we actually added. So if I'm trying to start a chemical reaction, I have to put in the right amount of a substance. See, I thought I put in 0.270 moles of calcium chloride, but I didn't. I actually only added 0.204 moles. I came up short. And the way this affects the reaction, think of it like the gas in your car. If you thought you put in 2.7 gallons, you can drive for, I don't know, maybe 50 or 60 miles. But you actually put in 2.0 gallons, you're going to lose a couple of miles. Just like this chemical reaction can't go as far because we came up short on the reactant. This is the fuel that goes into it, and we came up short. So let's see, where is this thing? There we go. So what happens is that if we forget to include the hydrate portion of the compound, we end up with a falsely high amount of the compound. I thought I had more than I did. And excuse me. So here's kind of a summary of what happened. We added 0.204 moles when 0.270 moles were required. So we are quite a bit short.